Now we're going to look at another problem. This problem involves a little bit different way to figure out values of the trig functions. So in this problem we know what quadrant the angle is in, and we also know the value for the tangent of theta. So let's draw the picture. If this is in quadrant 3, that puts the terminal side of our angle down here. And let's look at this like a problem where we have the point xy, and we're trying to figure out the values of the 6 trig functions. Now if we knew the values of x and y, and found out the value of tangent, and it turned out to be 8/5, the question is, how could that happen? Since this is in the third quadrant, that means both the x and the y have to be negative. So one way we could get a tangent value of 8/5 would be if x were equal to -5 and y were equal to -8. Since remember, the tangent of theta is y over x. So that would give us -8 over -5, which would simplify to 8/5. So if we go with this, if we have the x and the y, that means we can find the r, and then we can find the values of the other trig functions. So we're going back to our definitions. R is the square root of x squared plus y squared. We have -5 squared plus -8 squared. Remember, when you square a negative number, you get a positive value. That gives us positive 25 plus 64, which gives us an r value of the square root of 89. So now we can find the values of our other 5 trig functions just by using our definitions. So we would have cosine of theta is x over r. We said our x was -5, so that would be -5 over the square root of 89. Again, if we're trying to rationalize the denominator, we would want to multiply the top and the bottom of this by the square root of 89. That would give us -5 times the square root of 89 over 89 for our cosine value. For sine of theta, we would have y over r, which would be -8 over the square root of 89. Same thing for rationalizing the denominator. We would take the top and the bottom times the square root of 89. That would give us -8 times the square root of 89 over 89. Then for the tangent of theta, this is y over x. We already knew this one, but we can do this just to check it. This would be -8 over -5, which would simplify to 8/5. For our other 3 functions, we can use our reciprocal definitions. So for the secant of theta, it's the reciprocal of cosine. So if we took our original value for the cosine, it was -5 over the square root of 89. We can just take that and flip it over. That gives us negative square root of 89 over 5. For the cosecant, we can do the same thing with our sine value. So we're going to take our original value here and just flip it over. That's going to give us negative square root of 89 over 8. And then for cotangent, we can take our tangent value and flip that over, which gives us 5/8.
Now we're going to look at 2 different types of identities.
The first type we're going to talk about is called the Pythagorean identities. The reason they're called that is because we use a right triangle and the Pythagorean theorem, which says that a squared plus b squared equals c squared. Where this comes in with our trig functions is what we've already been using. That's the idea of the point x, y that's on the terminal side of the angle. We use that to form a right triangle, so we have x squared plus y squared equals r squared. We're going to use this to simplify some expressions with trig functions, and we'll get some identities. That's why they're called the Pythagorean identities. So the first one that we're going to look at is this expression, sine squared theta plus cosine squared theta. We're going to look at the definitions of these 2 trig functions and simplify them, and then use our Pythagorean theorem to simplify them even more. So first of all, we can rewrite sine squared as sine theta squared. We can write cosine squared as cosine theta squared. Now the next thing we can use is the definitions of our trig functions in terms of x, y, and r. So sine of theta is y over r. So in place of sine of theta, we would have y over r, and that's squared. Cosine of theta is x over r. So we would have that quantity squared. And now we're going to work through this and simplify it as much as we can. So first of all, we would have y squared over r squared. Then we would have x squared over r squared. Now, since these two rational expressions have the same denominator, we can write this as one big rational expression. I'm going to do this, and I'm also switching the positions of the x squared and the y squared. So we have the x squared first and the y squared second. Now we're going to use our Pythagorean theorem. We know that x squared plus y squared is equal to r squared. So we can replace this whole numerator with r squared. Then we have r squared over r squared, which is just equal to 1. So what we end up with for this first identity is that sine squared theta plus cosine squared theta equals 1. So when we talk about an identity, we mean something that's true no matter what the angle is. As long as we have the same angle for both of these, if we square sine and square cosine and add those two together, we always end up with 1. The next one we're going to look at is this expression, tangent squared theta plus 1. We can do the same thing with this one. So we can write this as tangent theta quantity squared. Then we can rewrite tangent theta with its trig definition, which is y over x. We can simplify this to y squared over x squared. And then these two, we need to get a common denominator. That common denominator would be x squared. So we're going to multiply the top and bottom of this by x squared. That gives us y squared over x squared plus x squared over x squared. So again, we can write this as one big expression. It turns out to be x squared plus y squared over x squared. The x squared plus y squared we can replace with the r squared. So we have r squared over x squared. Now what we'd like to do is write this in terms of a trig function. What we can do is rewrite this as just r over x quantity squared. R over x, if we go back and look at the definitions of our 6 trig functions, this is actually the reciprocal of cosine, which makes it secant. So this is secant theta squared, or we could write it as secant squared theta. So this identity, what we end up with is tangent squared theta plus 1 equals secant squared theta. And again, an identity means that it's true no matter what the angle is. So no matter what theta is, this is always going to be true. Then the last one we're going to look at actually looks a lot like this one, only instead of tangent squared here we have cotangent squared. So we have cotangent squared plus 1. What we do here is going to look a lot like what we did up here. We're going to rewrite cotangent as x over y. That gives us x squared over y squared plus 1. Then we're going to get a common denominator. This time it's going to be y squared. So we end up with x squared plus y squared over y squared. That would give us r squared over y squared. We can rewrite that as r over y quantity squared. And r over y, if we look at our 6 trig functions, that is the same as cosecant. So our third Pythagorean identity is that cotangent squared theta plus 1 is equal to cosecant squared theta. So we have three Pythagorean identities. Of the three, the one that I want you to remember when you get out of this class, if you don't remember anything else, is this first one. Sine squared plus cosine squared equals 1. And here are the three identities written out for you down here. Now let's talk about the quotient identities. These ones again come from the definitions of some of our trig functions, specifically sine and cosine. So if we start with this expression, sine theta over cosine theta, and just simplify it by using the definitions of those two functions, we would have sine of theta is y over r, and cosine theta is x over r. If we simplify this rational expression, we can take the denominator and invert it and turn this into multiplication. That would give us y over r times r over x. Then we can cancel out the r's and we end up with y over x. If we go back to our trig function definitions, this is the definition of tangent of theta. So our first quotient identity is that sine theta over cosine theta is equal to tangent theta. Our second one is very similar, but it's just that expression flipped over. So if we look at cosine theta over sine theta, we rewrite these functions in terms of our triangle. We would have x over r on the top, y over r on the bottom. If we invert and multiply the y over r, we would get x over r times r over y. We can cancel the r's, and that turns into x over y. X over y is the definition for cotangent of theta. So our second quotient identity is that cosine theta over sine theta is equal to cotangent of theta. And with these two, notice we can use these in either direction. So if we end up with something that's sine theta over cosine of theta, we can simplify that to tangent of theta. Or if we have one of these two functions and we want to rewrite it in terms of sine and cosine, we can go the other direction. So we can go from tangent of theta to sine of theta over cosine of theta.